My name is Hannes, and I'm here today to talk about DuckLake, a very new thing. I think it was released 2 or 3 weeks ago. The time flies, and it is about Lakehouse formats, right? And I'm going to take you, explain what that is and how DuckLake is different. But it is really built upon these principles of, being usable for everyone, right? And so actually that's something that, my previous 2 linked list entries also really value, is to make things that people can actually use and their work. And that's also very much a priority for us. A little bit about myself. This was my first car, not this very one, like mine was much rustier. But the license plate was real. So I've been doing like SQL stuff for a while now. I think this was like 2003 or something like that. But it had the love of structured, queries, tables, and things like that has stuck with me. And I need to address like a little elephant. I have been not a distributed systems guy, let's say. I've been quite vocal for my, dislike for people to default to distributed architectures without thinking twice. Just a few weeks ago, I declared my sort of, problematic relationship with distributed systems at Data Council. But in my defense, I did write a thesis about distributed query processing way back when. So I was there 3,000 years ago, I think is the quote, but then decided to go elsewhere. And that has to do with simplicity, with my love for simplicity. Some people here might actually know DuckDB. You can maybe raise a hand if you know DuckDB. Oh, very good. Who has used DuckDB? Okay, it's almost as many. That's excellent. Thank you very much. You make me very happy. So some of you might know me as one of the people behind DuckDB, which is a universal data wrangling tool for largish sort of data sets. And it's one of the things that comes from Amsterdam. So we're here in Amsterdam. It was mentioned, and it's like used all over the world, which gives us great pride because usually technology comes from somewhere else. Yeah, it's true, no? I mean, which software projects you know from Amsterdam? Who knows another software project from Amsterdam? Python, exactly. Okay, that's a good one, yeah. But we'll move on to lake houses. So this is a lake house. Yeah. And I love the picture, even though it doesn't look as great on this gigantic screen. What is this about? And I know there's been a lot about like hype around things like Iceberg and Polaris and Delta Lake and Unity and Hoodie and God knows what. But I'm here to kind of walk you through sort of the original sort of the rationale behind Lakehouse and why people are actually interested in it, and then tell you how DuckLake kind of improves on these things. So this is a Lakehouse. Just for the people who don't know, it's kind of the word comes from saying we used to have a data warehouse that's old and busted. Who wants to have that? And we have a data lake that's cool and hip, but a bit unruly. And if we merge these 2 things, we get a lakehouse. One of the things I really hate about these people that came up with this term is that they ruined the actual lakehouse term. So if you now Google lakehouse, you find a lot of Databricks stuff, but not this anymore. And I hate that. Anyways, so to understand the lakehouse, we have to understand where it comes from. In the beginning, there was a single computer, and it had in it, as Mr. von Neumann, Dr. von Neumann, has commanded, storage and compute. So we have some computers, this little chip icon there, and we have some storage. That's the little stack of disks. And they are in the same place. They are in the same computer, same physical hardware. So this is, even if you go back all the way to the origins of digital data management, which, by the way, came from the Apollo program, believe it or not. This was the setup, right? Computer, disk, compute. Okay? That was really great. I'm not going to go into replication, but it's also still what we have if you run like a Postgres server, right? You have one box has storage and compute. Then these pesky distributed people came along and say, aha, but does it scale? It's one of my favorite battle cries, but does it scale? Like I'm gonna, at some point, I'm gonna sort of develop sort of a aggressive reaction or something to somebody who's asked me, does it scale? Because usually the people that ask me this question haven't fully sort of understood the problem. Anyways. So this is when, you have, maybe you remember systems like Greenplum or Teradata. They said, we'll scale out this data warehouse thing that was on a single computer by having more computers. Okay, that's great. And this is called a shared nothing paradigm, where there is a storage and compute like independent on these computers. And there is a king. We're in the Netherlands, so I figured we can have a king, right? He's a king. The king is, or the queen, is basically a centralized piece of sort of metadata storage, okay? So where we kind of keep track of which computer has which bits of the data, and we keep track of maybe tables exist and things like that. So that worked really well. Then we got a bit distracted by taking this exact architecture and ruining it with Hadoop by basically saying, you know what? This was way too structured with these like databases there. Let's make it worse, way worse with text files. Okay. Thankfully the world has kind of moved on from this, but I just wanted to mention this as a sort of sideways thing. Also, whoever designed this logo should, I don't know, dude. It's like, look at it. On to some better logos. So here we have the sort of the next iteration of data warehouse architecture, where the major innovation is to disconnect storage and compute. And this is something interesting, because it took me forever to accept that storage and compute should be disconnected. I think Jordan is here somewhere. There, he's said this for many, very early on, we should disconnect storage and compute, and he was one of the people behind BigQuery. But basically that says we'll take, we'll forget about shared nothing. We now get shared storage, because we have, very scalable storage systems. Today, you might think of object store systems like S3, but we'll put all our files in there, and we'll basically rely on the network being fast enough to get the data to these compute nodes that don't have storage at this point. They're stateless. And that was something that BigQuery did. Snowflake also did that very early on. And you still have this metadata node somewhere that has a database that stores, which tables exist, where the files are that belong to these tables, and so on. And this works really well, because you can kind of have many compute nodes as you want, and as long as your storage sort of system that you now have abstracted away kind of does what you want it to do. And I know that's a big if. And I know there's a lot of sort of stories about how, somebody has been mistreated by S3. But in general, this holds. Okay, so this is the system architecture 2015 or something like that. Okay, so now we come to the Lakehouse world. Lakehouse world basically said, initially at least, no more kings or queens. Forget about this metadata node. This is evil. It's a database. It's legacy. Who here loves databases? No one. Okay? There's one person that loves databases there. I salute you. Thank you. But yesterday somebody told me that databases are considered legacy, and I'm like, yeah, it's a 5,000-year cultural technology. It's not legacy. Anyways, so they said, let's get rid of the database. It's evil, and it's not going to scale. And we replace it instead with these files. Okay, so now you see this little paper airplane. That's an Avro format. So we basically replace the database that tells us where what is, which is kind of critical task. We would agree, right? If we, where is what, which tables exist. We replace that with a bunch of files on object store, because object stores scale, obviously, right? So that must be a much better architecture. And it's not just one file, it's actually quite a lot, so we're going to zoom into this little cloud here, okay? Are you ready? Everybody ready? Yep. Okay. Bam. Yeah, who here has seen this picture? A few people. Okay, so this is actually, I love stealing other people's pictures, right? This is straight from the Apache TM, Iceberg TM specification. And this is explaining how they are able, or at least so they thought, how they thought they were able to get rid of this metadata database in their, system. Okay, so we start, we start on top. There's this little arrow. You see the little arrow over there, up there, here? Yeah. So from out of nothing comes a little arrow. And we'll get to that. And then it points to a metadata file. This is stored in the JSON format, by the way. You're laughing. You will not laugh in 5 minutes. This is stored in JSON. So far, so sane, yes? Okay, we have a metadata file up there that stores these as 0, as 1. These are so-called snapshots, because in a table format, what we like is what we can sort of have different snapshots of the state of this table, and we can switch around between those things. Great. So we start on top, we get the metadata file, and these are files, right? Every box is a file here. And then in that metadata file, we find another file name, okay? We find another file name that gives us a manifest list. And this is a Avro file. For those of you who think, what on earth is Avro? You are not alone. I was also, when I first saw this, I thought, what on earth is Avro? It's a little-known file format from the Hadoop world, It's like rearing its ugly sort of elephant head again. Why are you laughing? And this Avro format is then encodes the manifest list, which is kind of a list of files that are part of a table, and that then again has a file name in it, or several file names that points to another layer of Avro files, the manifest files, okay? And those again, in turn, contain a bunch of other file names, and in this case, they contain a list of Parquet files. On the very bottom is Parquet files. So this is kind of good, right? Like we like Parquet files at the bottom here. And then, but this whole list of files is only there to basically recover a sort of sane abstraction over tables that isn't sort of as chaotic as a sort of data lake, where it's just everything is a bunch of Parquet files. So it's trying to recover some sanity, some sort of logic about transformations, how like making changes to tables, like making schema changes, and so on. But it's doing all that with other files, okay? And when I first saw this, I thought, this is kind of sane. We have one abstraction, we have files. And if you want to make, if all you have is a hammer, if all you have is files, then making everything be a file is kind of logical. And then, I could kind of see this. It had a certain sort of elegance to it, in the sense that we only have these files, and we have compute, and that's it. Okay? So that was the first iteration of Iceberg. There were some tiny problems that I've glossed over here. One of the biggest problems that emerged early on was the little arrow up here. Hang on, how does this work again? Does this work? Why does this not work? Now it works. There you go. This little arrow up here. Like, how do we know which is the last version of this file? Well, the original approach was we just number them in increasing order. And then we rely on file listings to find the biggest one. That was a bit problematic, because object stores at the time had some issues with consistency on listings. So there was some problems with that. There were also some issues that, if multiple people tried to change anything here, it was a long and involved process, and it would usually conflict and fail because of it. So, the designers of Iceberg, by the way, $2 billion idea, it's a great idea, must be if it's worth $2 billion, thought long and hard, and they said, aha, we will solve this problem. We will solve this problem with something called the Iceberg catalog, or the Iceberg REST catalog, or IRC, although if you're old like me, IRC means something different. So we put this thing on top there, which is a it's kind of round, has a certain roundness to it, right? But of course, it's never enough in 2025 to put the database anywhere. You have to wrap it with some Java code because everything is better in Java, and it has to speak REST because everything is better when it speaks REST. So we add of course a Postgres, because in the end, what they did up there is they added a catalog server that basically stores a tiny table that keeps the current version of the table in it. Yeah? It's a single value. But since databases like Postgres are like pretty good at transactional semantics, now you have a single place where you basically talk to this single tiny table, find out which is the current version number of your iceberg table, and then you go do all this dance with the files again, right? But you will already have spotted the fundamental shift here. A database, a database? Really? So we are back to this thing, right? So we are back to this design, like the exact sort of design that we had before. Only we've gained another level of complexity, because you will see that we now have both a metadata server up there and a bunch of abro files on our storage. And they sort of interplay in a sort of unholy way. So there are several major problems, right? So you have the first problem is that Iceberg is a table format. People want to have multiple tables. Now you have this weird thing where the catalog manages multiple sort of things that are independent. And it's just going to be, by just adding this catalog, you're adding so much complexity, right? You're adding another thing that you have to host, maintain, upgrade, backup, failover, God knows what. You have huge amount of round trips. We'll look at that a bit more in a second, to read anything, because not only have you talked to the service, you still have to follow all of this dance down to the Parquet files, right? There's just lots and lots of gunk. I'm very sorry, but there is just lots and lots of gunk. I never will understand the decision of having 4 different encodings for data in one file format, right? You have JSON, you have abro, and you have Parquet, and you have the whole REST thing for the catalog. It's kind of crazy. The files down here, they're also, these metadata files are also really problematic to handle. They're either too big to be sort of read quickly. This can really easily happen with the metadata thing on top. Or they're too small, so object stores generally don't like dealing with a ton of small files. You have a lot of round trips. The Amazon charges you for those. So it's not really great. So what happened is that Mark and myself, we got together. This is very dangerous when Mark and I start to think. So we started thinking, and we were discussing all of these things, and we realized we have another splinter in your eye moment here. Okay? So for those who don't know this movie, it came out in 1999, I think. It's about somebody perceives something wrong with the world, for the young people. And this is exactly what happened to us. We were thinking about this, and I actually tried implementing this, and it was all there's something wrong here. You just told us you're doing all this stuff to not have a database, and now you're added a database back, but you never go back to your original design sort of decisions about not having a database and having all these files. That this doesn't make any sense. Okay, so now we come to DuckLake. After telling you all of these things about Iceberg, we're going to talk about DuckLake. And so this is really the next the next generation, which is, I'm really happy about this poster out there, of data lake setups. So what does DuckLake look like? DuckLake acknowledges that we need a database for the metadata. And we do not need a zoo of tiny files to store the metadata about our tables. So all the information about which tables exist, which columns exist, which files exist, which statistics can be derived from this, which partitions exist, all sorts of things are going to be stored in a database. It's amazing how obvious it seems after you design it. Okay, it's one of these things where we came out with DuckLake a couple of weeks ago, and the biggest reaction we got was "Oh, it's so obvious," and we're like, "Yes, but you didn't do it." It's it's a proven concept to have a metadata database, bunch of compute nodes, and object storage for storage. It's what BigQuery and Snowflake have been doing for 10 years now. It's really a super sane concept, and I'll talk a bit more about the scalability aspects in a bit. But just acknowledging you need a database with tables, and ACID, and like primary keys and things like that to store metadata, and you can kind of use the object store to store files. So this is really great and I know you would wonder, why do I do this, and why do I not just give Greenplum a lot of money, or what else, Snowflake? The cool thing about this setup is that we're kind of using commoditized storage for storing the actual table data. In the past, you would usually have this problem that you're basically using, like if you ever run a Redshift cluster, you know this problem, right? You're running basically Parquet on Amazon, and your actual table storage sits on these very expensive VMs. And if you have a ton of data that you're not actually using, you still have to run these very expensive VMs in Amazon. And with DuckLake, what you can do is you can say, I'm going to put all the actual sort of things that contain data, the table data, the Parquet files, in S3 object store. It doesn't have to be Amazon, can also be Google or Microsoft or your local host kind of thing. It's fine. And that's kind of it's a good sort of, it's been a price sort of, there's a very low price to putting a lot of Parquet files on S3 compared to putting it on Redshift. But if you then want to have more sort of query processing, you just add compute nodes as they are stateless. They can read from this, and it's really great. So I think it's really a great architecture for dealing with large amounts of table data. And let me talk through some of the principles behind DuckLake. We have some principles. First is simplicity. Then we're going to talk about scalability, because you're going to ask, does it scale? And then we talk about speed, because I'm a database person by heart. And in the end, if it's not fast, then it's really funny, because it's really the only thing in my life that I want to be fast. Like I drive a bike, okay? I have a very slow boat, but databases should be fast, okay? It's interesting how that works. Let's talk about simplicity first. I'm going to walk you through the very involved installation process to get DuckLake up and running, okay? Are you ready? Ready? Everybody's ready? Okay, you have to install DuckDB. There's various ways of installing DuckDB. This is the easiest one, if you trust us enough. Curl install duckdb.org, pipe bash. You can look at the script, it's fine. It just downloads our binary. So you do that. Okay, we've done that. We have DuckDB installed. Now we can launch it. The script installs DuckDB into this path, so you can just run DuckDB, and now you run DuckDB. Okay, that was it. You didn't have to install Java. Notice that you didn't have to install Java. You didn't have to install, Intel thread building blocks, runtime libraries. It's just running, okay? And then you just type attach DuckLake, metadata DuckLake as DL1, and that's it. So that's how you instantiate my first DuckLake, okay? That's it. That's really these 3 lines. And this is like a laptop that you've never done anything with data before. Works on Mac, works on Linux, works on Windows, doesn't really matter. So this is like really the first aspect of simplicity that we tried, was to get like the process of setting this up extremely simple. And I am somebody who has actually set up a iceberg stack by hand, and I can tell you, it takes a PhD in computer science and now a day of screaming to get this done. This is like 10 seconds, right? It's quite a bit difference. Next on for simplicity. Again, here's this picture from the iceberg spec again, and I try to redraw it, in the same style for DuckLake. So here's on the left we have the iceberg set up with the metadata catalog with the 3 layers of metadata files, and then the Parquet files on the bottom on the right. We have DuckLake, right? You can see that there's quite a huge difference there. We have a database and we have files. Wow, right? It's insane if you think about how many layers, how many tools, how many security problems you get for having 15 technologies in your stack versus you have a database and files. And now you say, but your database needs to be extremely complicated to map all this, enterprise-grade complexity here. No, I mean these are the tables. They're not rocket science. I can walk you through them briefly. On the very top, we have snapshots, basically, a state of the database. We have schemas, which is like a collection of tables. And we have tables, shockingly. So we have a table about tables. I like this. It's like inception of databases. And then in these tables there are a bunch of columns, shockingly. And we need to have some table that stores the names of these columns and the data types. And then under this sits a table that contains a bunch of pointers to data files and to delete files, because when in like these data lake in this Lakehouse formats, the deletions are stored by having separate file that points out which rows are deleted. And there's a bunch of other little tables around that, mostly about statistics and partitioning. So we have a bunch of statistics about like minimum and maximum value and whether there's nulls or not in these tables, and that's on a table level, on a column level, and on a file level. And so we can prune all of this stuff, right? So it's really simple. And we actually made this sort of simple on purpose, right? It's not like we tried to we used every single database feature we could think of, because we want this to be portable to many database systems out there. This should be possible to run anywhere. We also used really simple types. I think we used 3 types or something that everyone has. And at this point, I have to sort of also point out that DuckLake can be a bit confusing because it's both a standard and an implementation. Okay. So what is the standard? The standard is essentially this: the tables. We say, look, if you want to do a DuckLake, we agree on this schema. We agree on that we have to put a field ID in the Parquet files for the connoisseurs out there for every column, and that's kind of it. So there's a standard, there's a convention, there's a bunch of queries and kind of restrictions how you update this table. But then there's also an implementation. So we made the first implementation of DuckLake very shockingly in DuckDB, and I'm going to show you some examples later on. But it's important to differentiate that basically everyone can implement this. It's like Iceberg, right? Iceberg itself doesn't really have an implementation. There's one in Spark that they make, but that's a bit similar, right? Like there's a specification and there's an implementation that's kind of trying to showcase what it can do. So we have the same. So just to clarify this. But here's again a bit, on simplicity, the tech stack that you need to run like Iceberg is like you need a Postgres, you need Docker, you need Polaris, the catalog server, you need Java, you need like this REST stuff, you need JSON, you need Avro, you need Parquet, you need S3, and you need Spark, and you need all these technologies like working together well, which is actually quite difficult. And in DuckLake, what do you really need? Like you can run an entire DuckLake with DuckDB only. I just showed you the example. But you can also, if you want to go further, you can use other things to store metadata, you can use other things to store data, and so on and so forth. Like this is really, where I think the thinking about systems, like Joran has said earlier, right? Like cutting out things is making them better, like in my opinion. Like having fewer dependencies, having fewer things that can go wrong, having fewer like random Avro problems impacting the performance of your data storage. Okay, so that was simplicity. Now we get to the really important question: does it scale? So maybe we can do like a little. You can try to trigger me by chanting, "Does it scale?" Can you do that? 1, 2, 3. Does it scale? Thank you. So, does it scale? It's okay. Thank you very much. You have successfully triggered me into rage. Okay, does it scale? The answer is, of course, it scales. Otherwise, I wouldn't be making jokes about this. The interesting thing about DuckLake is that you have choices. So this is like, it's like a, what is that, the one-armed bandit thing, where you have like these, and actually there are 3 different dimensions that you can kind of choose by, ideally more coordinated than just pulling a lever and going. But there's 3 things you can kind of choose when setting up a DuckLake. Okay, and here we are back at the architecture picture. We can scale 3 things independently. The first is storage, okay? So very bottom here, you have the little cloud. You can put your storage on S3. Or you can put your storage on a Samba server, for all I care, right? You can put your storage on a local file system. I don't care. The point is that you choose which sort of storage you want to use. And it really can be anything. Anything that can store a file and read it back to you is fine, right? We don't need any we don't do moves. The files are always immutable. We never append to a file. So it really can be any storage. It's really open to, if you wanted to put your DuckLake storage into a key value store, by all means, right? Into a memcached, whatever, I don't care. So you can scale the storage yourself. And thankfully, I think with object stores, the scaling anxiety on storage has kind of gone away a bit, right? Like we are kind of used to being able to shove an infinite amount of data into S3. That's great. The compute. How do we scale the compute in DuckLake? Well, it's kind of easy. These are stateless compute nodes. We can have as many of them as we want, right? They talk to to storage, obviously. They talk to the metadata server, which could create load in the metadata server. We'll talk about that in a second. But yeah, again, you can run this in whichever compute you want. You can pick this. You can run like small VMs, large VMs. You can run lambdas. You can run some sort of medium thing. You can run this on like people's phones if you want to, right? Like this is actually, I'm going to talk about it later a bit. It's actually one of the cool things. It's nothing keeps you from running a DuckLake compute on a phone because it's just it's just DuckDB. It's not like a 15-layer tech stack. And then you get automatic scalability with the number of users. It's very cool. But the last thing we have to scale is the metadata server, and that is a fair point. We have to scale that. Thankfully, in the last, let's say, 10 years, we have made lots of progress with scaling sort of SQL-based systems. So you can use Postgres for this. I think if many people use Postgres for their DuckLake setup, you can use DuckDB for it as well. That also works. But if you ever run into sort of problems with your metadata server, nothing keeps you from using a Snowflake or a MotherDuck or a BigQuery even to keep your metadata for your DuckLake, right? So it's really something that you can just get a bigger database. And this is the metadata. This is really a small amount of data. It's not like this will kill you in terms of like cost. There's just choices. You can just choose because we don't tell you which database to run for the metadata. There's some very small restrictions. You have to be transactionally safe, so that rules out some systems out there. You have to basically support primary keys and data types like strings. Sorry, Jordan. Strings and integers and timestamps. I think these are the three. So let's look a bit at sort of like different sort of turns of the one-armed bandit here. So this is the simplest setup, right? Where you just say, okay, I'm going to have one single computer. I'm going to put my files on a local disk there, and I'm going to use DuckDB as the metadata storage. This is exactly what this attach command here does. It says, hey, attach a DuckLake here, and with this prefix DuckLake, if you don't say anything, us being DuckDB, we assume you want DuckDB. And it will just create for you a DuckDB file called metadata1.ducklake that contains the metadata tables. And in this case, it will even infer the data path as a variation of that file name, right? So it will just be a files on your computer. And that's really great for prototyping, right? This is like a one-liner. You set this up as I showed you set this up in 10 seconds. And then you can interact with it in the exact same way you would interact with it if it's a giant distributed system. So this is the simplest case. Now let's say you are like one of these paranoid organizations like a bank, and then you want to self-host all of this in your local network. You want to self-host a DuckLake in your local network, but you want to be able to scale compute, and that's really not a problem. What we have to do is we have to instantiate a separate metadata server. In this case, that could be Postgres. Really works well. So we have a Postgres, and we'd say we'll use a network file system, NFS, to store the files. And again, these are immutable. These are the files are mutable, and so we work around a lot of the consistency problems we usually get with things like NFS. And then we can just have a bunch of compute nodes, and on each of these compute nodes, we would just run this command, right? We instantiate a DuckDB or another compute system, and basically tell it, hey, you're going to talk to a DuckLake, and it's going to be a Postgres, and it's on this file, on this machine, host metadata. Okay. And then you have to specify the data path in this case, where we say, okay, and the data path is going to be on this NFS mount. Very simple. Now we say, okay, we are now in a not so paranoid organization, and we want global accessibility of our DuckLake. Well, that's not a problem. We just change some things in our setup here. It still looks exactly the same. Maybe the metadata server is now something that runs in Amazon-hosted Postgres or Neon or one of the million hosted Postgres instances out there. Why not? Or you put it somewhere else. Doesn't really matter. So you point to a globally accessible metadata server, and instead of having an NFS mount for your data, we'll now point to S3 bucket. And now you have a globally accessible, huge data sort of management system that, with like 2 little changes. So that's one of the really cool things I think about DuckLake, is that it can sort of is versatile in sort of the weight of its deployment. By just changing a few parameters here and there. And it's just, you point it to a metadata server, you point it to storage, and that's kind of it. And because you asked me, does it scale? Mark did a small experiment. So we took a petabyte of data. People seem to respect a petabyte, right? I mean, I don't know. I don't know what it is. It's super random, right? It's like, a petabyte is big, okay. So we have a petabyte of data. And we have an example data here. We took 10 columns, and then we made like 100 million snapshots, which is actually a pretty bad case. Like Iceberg would not be capable of this, right? We have 100 million snapshots, and we have about 270 gigabytes of data being added per day. So this is the example. And then we looked at the time it takes to do query planning on this. So as the query planning is the part that is like the critical thing that has to happen in the metadata server, right? Because like actually reading the data and actually running queries is something we can just have as many nodes as we want to. There's no problem there. But the metadata, the query planning happens in the metadata server with just a SQL query, by the way. How long does that take? Well, and if you do an insert, it's like 5 milliseconds or 3 milliseconds. That's pretty good, right? Like so, adding a new snapshot that inserts data is 3 milliseconds for a petabyte of data, right? It's pretty good. If we read all the files, again, this is the query planning time, not the query processing time, right? In DuckDB, this is like less than a second. Postgres takes a bit longer, mostly because we have to transfer, we have to read like 1 billion statistics entries or something like this for this. 200 seconds, but again, you're reading a petabyte of data, you probably can live with 200 seconds query planning time, just saying. If you select a single month of data, it's sub-seconds. If you select a single day of data, it's sub-second. And that really sort of matches up with the pattern that we see a lot in how people access these large data sets, is that they're mostly interested in the last month or last year or whatever. So that's really interesting. So this is really the worst case scenario for the catalog, where we have a huge amount of snapshots. And again, DuckDB can handle this no problem on a MacBook. Postgres. We did some minor optimization, like partitioning some tables and adding an index. Hey, it's a database, You can add an index. It's amazing. Okay, so that's scalability. And now let's talk about speed. So there's some aspects of talk about speed. Let's just start looking at speed from a purely off the boat, sort of conceptual view. We look at these pictures, this picture again. And we have Iceberg on the left, and we have DuckLake on the right. And I've added a little laptop there. That's our client. That's the thing that tries to read something. On the left side, in order to read anything from an Iceberg table, you first talk to the catalog server. Again, you have to instantiate a Java thread and stuff like that. First talk to the catalog server to get the current snapshot number. Then you do a read on the storage to get the metadata file. Then you do a read on the storage to get the manifest list. Then you do a read on storage to get the manifest file or files. And then you do a read on storage to get the Parquet files. And this is things that cannot be parallelized because they're dependent on each other. There's a data dependency in there, right? Yes, you can parallelize the reading of multiple data files, great. You can parallelize the reading of multiple manifest files, great. But you don't know which ones you need until you read the manifest list. So that means that we have to add up all these latencies of these 5 steps together. That's not great. On the right side, what do you do to read something from a DuckLake? Well, you talk to the database. We just saw that's like sub-second kind of thing. And then you read the data files from storage. That's it. End of checklist, as they say in aviation, right? So this is going to have some impact on performance, right? Just from this, you already know that one of them has to be faster. Just if you put your what could you possibly do in terms of in terms of sort of engineering to make the left side faster than the right side? I don't think there's anything you can do, because in the end we're doing the same thing. We both talk to Postgres. In the end we both talk to Postgres, and we both talk to object store. Only that Iceberg needs to do this 4 times, and we do it 1 time. Okay, and I did a benchmark, because I cannot in good conscience have a database talk and not give you benchmarks, right? Like it's just in our nature. Like you will just not be able to stand up in front of a group of people without a benchmark and not feel naked, okay? It's in our little database nature, what can I say? But then I also need to preface this with our paper that says fair benchmarking is difficult, common pitfalls in database performance testing, and I would like to point you to this wonderful plot on the right here, where it's our system is fast and their system is slow, okay? This is just as a preface, and I know it's very difficult to make fair benchmarks, and I wanted to say this to kind of, to point out, yes, it's very difficult to do benchmarks, and we try really hard and we get it wrong sometimes, so, yeah. It's not a end in itself, but I couldn't resist of doing a benchmark, because I looked at this picture and I said, well, no matter what we do, we're going to be faster than this, right? And here's the result. So this is a plot of us running a benchmark where we have an Iceberg table. This is the green dots with the Iceberg REST catalog and an object store. In this case, we set up everything on localhost. And this is actually benefiting Iceberg quite a lot, because our network round trips are very fast. So they don't get punished as much as they would if they were on different boxes. So this is all local. We have a local catalog running, we have a local S3 clone running, and we have a local Spark cluster running. All local, it's not really a cluster. Local Spark running to do updates. And what do we do? What is the workload here? We use TPCH. Of course, we did TPCH. Scale factor 10, which is like 10 gigabytes of about 60 million rows in the line item table. And then we do updates. Like this benchmark also specifies what updates should look like, and we generated 100 updates, which are just insertions into that line item table. Every update is about 2 megabytes per case, so not very big. And then we just measure the wall clock time. So let's look at this. So DuckLake is about 4 times faster in this best case scenario for the Iceberg stack, right? Where it's all local, they don't get punished by round trips. There's just, and this is also, we can also see that the DuckLake time is much more stable. I mean, some evil people out there might say this is just because Java, but I think it's also because there's just much less moving parts, right? It's just 2 things. And the benchmark also specifies deletes, right? So this would have been a really great benchmark to also add deletions, because that's one of the more complex operations on these Lakehouse formats. However, I actually managed to crash the JVM by running the official Iceberg Spark plugin on my laptop, which I have not seen in a while, right? This is actually the JVM going down on my laptop here, when I tried adding deletes, when I tried doing deletes in my benchmark, and I was absolutely amazed by this, because I thought, how on earth has nobody tried this, right? this is the first thing you try. It's the first thing I tried, and hey, it's reproducible. If anybody here works for Databricks, you come talk to me. Yeah, so that's Iceberg. That's DuckLake. I'm gonna do some speed run for feature highlighting that DuckLake has. So DuckLake does multi-table, right? Like the Iceberg format itself is limited to one table. We can have as much tables and as much schemas in one instance as you want, and it's all multi-table transactions, not a problem. We have holistic transactions. We can, like a normal database, you can have 15 different modifications. You can create tables, you can change tables, you can insert, you can update, you can delete, you can drop. It's all in one single transaction because we just run one single transaction in the metadata store. It's a database, it can do that. It's really great. We have time travel as well, right? Because we have all these snapshots, we can query tables as of a specific snapshot. So we can say, read from this table at this version number or at this timestamp. It's really useful for stability in the in queries or in results. We also have a change feed. So if you use DuckLake, you can use this little magic table changes function there that gives you, in this case, all the changes happen to this table between snapshots 3 and 4. And obviously, it's all tables. By the way, these are all tables. You can query them and find out things about your snapshots and which snapshots you want a delta for, and when they happened, and all these things. It's all just tables. There's no API other than the one that we glued on top with SQL. You can query all of that. It's all transparent. Here's a really cool feature that Mark built recently. It's called inlining, where we realized one of the big problems of these Lakehouse formats is small appends, right? If you add a single row in a snapshot, it's going to kill you because you're adding a Parquet file, you're adding the manifest, you're blowing up all this file zoo, and you have a Parquet file with one entry in it in the end. It's not great. And DuckLake, of course, if we were to write a Parquet file for every single one row insert, it would also be problematic. So what we do is we actually say, hey, we have a database. We can buffer some rows in there. So we have this thing where you can basically specify a row limit for insertions that are actually not going to your object store. They're going to stay in the database, and you can flush them later because why not? We have a database. And this is really cool because this also follows all the transactional guarantees, and the changes are immediately visible. It's not like your standard sort of have to catch up. You have to wait for the Kafka queue to overflow, and then it gets flushed. No. This is just immediately there. Also, something that is really cool is encryption. So you can just basically you put one word here. You say encrypted, and what happens then is that DuckLake will automatically generate a separate encryption key for every Parquet file it writes, and store that in the metadata catalog, and then automatically uses this when you query it. And that's really interesting because it means you can actually store your table data on non-trusted storage. As long as your metadata service is trusted, the files are completely useless to anyone without these encryption keys. And that's actually using a Parquet feature that we just use. Parquet has support for encryption. It's really cool. I mean, I haven't really grasped yet what it means to run trusted, sort of to store secret tables on untrusted storage, but I would love to investigate. Interop. So we have actually our Parquet files in DuckLake use the exact same format, like Iceberg, including the deletes, and that means that we can do an in-place import from these formats. And we're actually working on Iceberg and Delta Lake import and export functionality, and it's coming soon, TM, right? So basically, you will be able to take an Iceberg table and just put it in DuckLake and then do some changes to it and push it back. Might be a really interesting use case for a longer sequence of local changes that you want to make. And finally, it's free. DuckLake is part of the DuckDB Foundation, which is an independent non-profit here in Amsterdam, which is it's released under the MIT license. It's an open specification in the sense that we release all the specification how to make your own implementation of DuckLake, and it's just you can do whatever with it. We're not going to stop you. So that's really great. Okay, so in the last couple of minutes that I have before the evil counter runs out here, I want to talk about what this means for DuckDB. So I'm coming back to DuckDB, sort of going back up into the sort of the old world of my life, pre-DuckLake. Here we have the 1985 data architecture. It's, again, it's a variation of the same picture. We have the mighty data warehouse. Again, that's all the stuff we talked about before. The mighty data warehouse sits on top, is the king. And under there, we have a bunch of application servers, and under there, we have a bunch of clients. Like already the arrangement like this shows you who's boss, right? It's the thing, it's the mighty data warehouse up there. And that's really bad because you're scaling 2 layers and you don't know how to scale these 2 layers independently. It's really bad for analytics because you have really slow paths of the data through there. It might work for WordPress, but it doesn't really work for anything else. That was 1985, conveniently 40 years ago, yes. I talked a bit about the 2015 data architecture where we have the exact same thing, but we now put our files on object store, and we have a mobile client. You saw it? It's there. It's like, that's the exact same thing. But I think what's interesting about DuckLake is it really turns this completely around. And I would like to claim that the 2025 data architecture is actually empowering the client, it's flipping this thing upside down, where now we have the devices or the applications or the processing jobs that need to access data are actually empowered because they are no longer sort of on the bottom of this food chain, but they are independently talking to a metadata server to fetch some information about where we find some data for a specific table. They can independently then go to object store and fetch Parquet files to read. They can also independently stage changes to that object store and then communicate with the metadata server to do a commit. And it's all really nice in terms of synchronization because you have these transactional guarantees on the metadata server, so you know that there can be no conflicts in commits. And obviously, I would like it very much if you would use DuckDB for this architecture, and if you would use the DuckLake abstractions for your metadata. But I'm going to zoom even further up. So our mission at DuckDB Labs, a company I work with, is to really change how people think about dealing with data. And we are trying to go from this current setup where I am fearing even like setting up my Iceberg REST catalog locally. People fearing data sets because they're too big, too expensive, too hard to use, like you're just afraid of them. Into this new world of confidence working with data where you know that you can throw it, this Parquet file or that weird CSV file at DuckDB and it will just work. And DuckLake is another iteration on this where we can build a centralized but highly scalable data storage systems using an abstraction that you understand, that you're comfortable with, that's robust, that's simple, that's just all of these things. So that was it. That's DuckLake. The website is ducklake.select. It's the coolest domain ever. Yeah, happy to take questions. Thank you.